Okay, guys, so let's keep going on this chapter 4 about ergodicity, which is central for this course. So recall the definition. Just, you can remember this. If you have an invariant set, then this has to have measure 0 or 1. Okay? And another important property that we used last time is that, if you have if the measure is ergodic, then invariant functions are constant. So you also have to remember this. Are constant almost everywhere. Almost everywhere. And also last time we have seen using this characterization r theta. So this is the circle rotation is ergodic for theta irrational. Okay, as I was saying last time, so throughout this course, the examples I will give are, these type of example which are system that, you don't have any expansion. This is a rotation. And also today we will focus mainly on expanding maps on the interval, particularly full branch expanding maps, and I will give the general scheme of proving ergodicity for those type of systems. And that will include, for instance, the decimal expansion, the Gauss map, and full branch maps in general. Okay? And so before I go to expanding maps, I should mention that there is also another way to prove this using Lebesgue density point. So an alternative proof of this one is using Lebesgue density. So the definition. So X in E, that is an element. Here I'm on the interval, okay, is a Lebesgue density point if the limit when epsilon goes to 0 of, I write lambda as the lambda is here the Lebesgue measure, okay, over 2 epsilon is 1, okay. And there is this fact that if you have positive Lebesgue measure set, then almost every point is a Lebesgue density point. So if lambda of E is positive, so lambda is Lebesgue here, then every point, or almost every point, sorry, then Lebesgue almost every point, lambda almost every point, so every point in E is a Lebesgue density. Yeah, for instance, if E is an interval, this is obvious, okay? If E is an interval, this is obvious because almost every, we say almost every point is a Lebesgue density point. You don't take the boundaries, okay? You just take them out. You take any point in the interior. This will, for some epsilon, this will be part of the set, and this is just 2 epsilon. in general, you use the fact that the interval, they generate this algebra, the sigma algebra, the Borel sigma algebra here, okay? So another alternative proof, so a different proof of ergodicity of R theta. By the way, again, to prove also ergodicity, it's enough to check these properties on a set that generates the sigma algebra, okay? So for that, we can just check this is true for intervals, and then you will get it for general measurable set, okay? So to prove this, R theta is ergodic. So you pick a set, let E be an interval, okay? Be in S1 interval, okay? If you do it for interval, then you can get it for every measurable set by using the fact that it generates this sigma algebra, okay? So suppose that this set is invariant. Suppose that theta minus 1 of E equals E, and let's also suppose that by contradiction that this has measure. So when I have an interval, I write lambda of E to be just, you know, like this. I can write it like this because it is an interval, okay? Let's suppose that this is in 0, 1, like strictly. So this also will imply that the complement of E has measure in 0, 1, okay? Okay, the complement is an interval. It can be unions of two intervals, or yeah, it's also an interval. I'm on S1. I'm not on 0, 1. I'm compact here, okay? So if you pick now a point, you want to get a contradiction from this assumption. So if you pick a point, let y0 in E complement, and since this is an interval and the measure is 0, 1, I can pick a point in the interior, x0 in the interior of A. Okay? So here the key property that uses irrationality of theta is that every orbit is dense. Okay? Every orbit is dense. So R theta in R minus Q imply that this guy R and theta, we have proved this of x naught is dense. Okay. So in particular, it's going to meet any small interval around y naught. So for every epsilon, there exists k n epsilon such that R and theta of x naught n epsilon is in y naught minus epsilon, y naught plus epsilon. Okay, this is just the definition of being dense. So in particular, what you have is so this guy lives is Lebesgue invariant. R theta is just a translation. So if you look at the size, the measure of this interval, y naught, x naught, y naught minus epsilon, and then y naught plus epsilon intersect with A, over 2 epsilon. So this, because Lebesgue is invariant, this is r theta and epsilon of, oops, sorry, x naught. Sorry, I mean x naught here. That's what I mean. X naught. Yeah, I mean x naught here. Sorry, because I want this to end in A. And yeah, I'm saying that this, they have the same measure because r theta is just a translation. I'm saying nonsense. I use E and A because in my notation I have A over 2 epsilon. And you can see that because of invariance here, you can just write this as r, sorry, the measure of r n epsilon theta of x naught minus epsilon, x naught plus epsilon intersect with A over 2 epsilon. But what happened is that this goes to 0 when epsilon, well, it goes to 1, sorry. It goes to 1 when epsilon goes to 0 because you are in an interval, sorry. This goes to 1. But what you know is that this orbit here is going to enter the complement here, okay? And this gives a contradiction. This contradicts that E intersect E complement is empty. Okay. Yeah, this is a more direct proof, but it requires to at least to check that. I want you to check that for ergodicity, it's enough to check it for a generating set of the sigma algebra, and also that you have this Lebesgue density for. Yeah, for the interval you don't need to check because for the interval every point is a Lebesgue density point. Okay, for an interval. Yeah, as I said, this is a type of example in dynamic system that doesn't have any chaotic behavior. If you want to say, you don't see any expansion. Okay, later on we will see that, you know, these type of systems, they have like zero entropy and stuff. After that, we want to see examples of expanding maps. In the, here, I will do something a little bit different from the book. Expanding maps. Okay. Yeah, in the book, they treated, the authors treated the 10x, the decimal expansion, Gauss map, and so on. So I will just give a method that works for all full branch expanding maps here. Okay. So I will recall full branch map. So this is a, so you have an interval, and you have f from the interval to itself, and you have a partition P that is omega I, omega alpha. Alpha is in a set of indices, so I don't know how to say this. In A is a set of indices. It's countable, okay? A is at most countable. It can be finite. Okay, and then you have, these are intervals. I'm just recalling because we have defined this. And that f restricted to the interior of omega from omega to I is a bijection. So this was the definition of full branch map. Okay, if you want, you can see that examples. We know the decimal expansion. And also the continuous fraction expansion or the Gauss map. this is also an example, and there are many more examples. So I will give a method that that works in general for. It's not done exactly like that in the book, but if you're following the book, in the part when they do the Gauss map, they use some properties that is really what is needed for the general argument to work for full branch expanding map, which is a distortion, bounded distortion. Okay, but before we talk about bounded distortion, I want to define a refinement of a partition. When you have refinement of a partition, when you have a full branch expanding map, full branch map, I haven't put yet expanding, full branch map. So we have these guys that goes to the whole thing. So in general, we have F, I in a partition. Okay, so this is full branch map. Now for every n, you can define a partition Pn. So for n greater than 1, we can define Pn omega n alpha, where alpha is in the set of indices. Okay, and how is this defined? Is just you take pullbacks of omega n equals the intersection of I equals 0 to n minus 1 f minus I of omega. So how is this? This is omega intersect with f minus 1 omega intersect f minus n plus 1 omega. Okay. You know, if you look at 2x mod 1, for instance, mod 1, you have p that is 0 half and then a half 1. P1 will be 0 quarter, a quarter, half, 3/4, and then 3/4 and 1, and so on. You can see Pn is just 1 over 2 I plus 1, 1 over 2I. Am I? No. Did I do this correct? No. Yeah? Yeah. Yeah, always when I do this, I confuse this with the Gauss map that have this. So this is not the partition I want. So what I want, I want I and I plus 1 over 2 to the I, yes. I equals 0 until n plus 1, n minus 1. Okay, and a remark is that, you know, if you look at Fn restricted to omega n, this guy is a bijection. Okay. So whenever you have a full branch map, you can define this partition. In definition of bounded distortion, this is a condition that is very important in dynamics. Bounded distortion. So let's suppose that we have f I p. I define it for interval, but you can define it for higher dimension also. A full branch and let's suppose that f restricted to each omega I is C1. So f restricted to omega alpha is C1 is differentiable. You define, so we say that f has bounded distortion if this quantity is finite. D, it looks crazy just looking at it, is the supremum over n and the supremum of omega n in Pn, and then the supremum of xy in omega n of log of fn prime x over fn prime y. So if this quantity is finite, we say that this map has bounded distortion. So this is just saying that, so for instance, if you look at this quantity, just look at this. Just looking at this quantity, not putting some condition on x and y, when n goes to infinity, you expect these two to be, you know, to look some like very different. They might go to plus or minus infinity, okay? But the way these partitions are defined are the points in omega n, they almost have the same type of itinerary until n step, because until n step they don't separate much. They are just on the interval, okay? They don't do something very different. So this partition is a way to capture, like, to divide your dynamics into orbits that stay bounded to each other until time n. So that's what this omega n is doing. You know, you take your space, you chop it into pieces, and in each piece, those points, they have the same feature up to time n. Now, for those points to have the same feature up to time n, you want to put that not only their feature, but also their first order, like their derivative also, is comparable. That's what bounded distortion means. And it's a natural condition, because if you say I chop my space, I have my interval, I chop it. So I want this guy, I say up to time n, I consider these points as 1. This is considered as 1 point at time n, up to time n. Therefore, it makes sense to also think that their derivatives are also comparable. That's what bounded distortion means. Okay, it's a very, important condition to have when you want to study invariant measures, ergodicity, mixing, many properties. This is a key condition. A way that this fails, a way to fail this condition is that, so if you have maybe infinite derivative, like if on the boundaries of this omega n, of these intervals, of this partition element, the derivative is infinite, okay? Like the Gauss map might, looks crazy, because here you have infinite derivative near 0. The derivative is infinite, but even though we can check that this is true, the bounded distortion is satisfied for the Gauss map. One way to think that this fails is to have infinite derivative, okay? To have infinite derivative. Okay, so this looks like artificial condition. But let's see this consequence, the consequence of this bounded distortion here, and that will give some intuition behind why remark is that if this guy FIP has bounded distortion, I'll be writing BD, okay? Then you have that E minus D J prime over J is less or equals to Fn J prime over Fnj so these are intervals, J and J prime, and J prime is a subinterval of J, okay? So, why this is true is just by mean value theorem, okay? This is just, so to see this, indeed, so this follows from mean value theorem, okay? From mean value theorem, meaning, you know, you consider the size of the interval is like the derivative times, so yeah, let me just write it, the size of Fn J prime equals Fn prime at the point xi, let's put J first, times the size of J, and also the size of Fn J prime equals the size of Fn prime xi prime of J prime, here for some xi in J, and here xi prime in J prime, okay? This is just mean value theorem, and then you can do the ratios and use the fact that these two are comparable to get this. Okay, it's just mean value theorem. All right. Yes. So now, why this condition is important now? That's what I'm going to write here. Is this theorem here? Theorem. I don't think they have this theorem in the book. If P has bounded distortion, then Lebesgue is ergodic. Then Lebesgue is ergodic. There is a warning here that Lebesgue is not necessarily invariant, okay? Lebesgue may not be invariant, okay? So this is a little bit against what I was saying at the beginning of this chapter, that I only consider invariant measure when I talk about ergodicity, but the definition doesn't need invariance. The definition of ergodicity, I erased it. So definition is just, you know, f minus 1 of E equals E implies that mu of E equals 0 or 1. But yeah, how is it useful to finding an invariant measure that is ergodic now? Before I prove this theorem, let's see this remark here. remark that if you have two measures, if μ1 is absolutely continuous with respect to μ2, and if μ2 is ergodic, then f μ1 is also ergodic. Okay? So if you have two measures, one is absolutely continuous with respect to the other, if this guy is ergodic, then the other one also is. Okay? And from when we were talking about invariant measure for this full branch map, if you remember, we have the parent Frobenius operator, and that's an operator in general for these expanding maps. It captures an invariant measure that is absolutely continuous with respect to Lebesgue. Then if you have Lebesgue is ergodic, so you will have also that invariant measure will be ergodic as well. Okay? So that's why this is useful. So let's prove this. Is this clear?
Which is absolutely continuous.
So that means that μ of 0 here implies μ.
Or the remark itself. Why it is clear exactly?
Well, is it clear that if μ2 is ergodic, then μ1 is ergodic? This.
Yeah, I think so.
Yeah. Yeah. Okay, let's prove this theorem here. Using bounded distortion, the proof is just simple. Since we are here on the interval, we can check that this is true for AE is an interval. Okay, so let E interval such that f minus 1 of E equals E. So now we want to prove that the measure of E equals 0 or 1. Or let's suppose that this guy has positive measure, okay? It's not empty. And we want to prove that the complement has 0 measure. Okay? This is really a one-line proof, basically. If you look at now E complement, the proportion of E complement on the interval, and this is just, okay, I minus E of I. And since we have a full branch expanding map, this you can write it as f n omega n restricted to E over f n omega n. Because this is just I. Because by definition of a full branch map, this refined partition, it has a property that after n step is going to be mapped to the whole interval. So this is I. Okay, up to 0 measure set. This is I. So I should be very rigorous here. I should say from the interior of omega to the interior of I, okay? Just to be precise. Okay, but the interior and the set, they have the same measure. These are intervals. And by invariance, you can write this as Fn of omega n minus, I don't know why I do this, I should have done this, E over Fn of omega n. Okay, this is because of invariance, and this is true for any omega n. Okay, this is for any omega n, because any omega n you choose is mapped to the whole interval. And by bounded distortion, BD, you have this is omega n over by bounded distortion. And if E complement has some measure, you can choose this to be in E. Sorry, this guy has positive measure. You can choose this to be in E so that this guy, it goes to 0 as n goes to infinity. Because this guy, you can choose omega n that is in E, okay? That doesn't, so that this guy is arbitrarily small compared to this one. This is true for any omega n. Okay, this is really a one-line proof. Now, this bounded distortion condition, it looks like I mean, looking at it like this, it looks like something to be difficult to check in practice. So let's find a condition that implies bounded distortion. But before that, maybe I have a So the point of having this theorem, let me remind you that the point of having this theorem is that once you have it, you have another measure, the invariant measure that is another invariant measure that is absolutely continuous with respect to Lebesgue will be ergodic. Okay. So there is this problem, or that can be good for a presentation, that every full branch expand. I haven't defined expand. I would tell this problem maybe in 20 minutes. Sorry, I'll say it in 20 minutes. I was writing a word that I did not define properly. I will define it and then, yeah. Okay. So yeah, a condition. Let's see a sufficient condition to get bounded distortion. I have been saying expanding maps without writing a full branch map. I don't need to write a full branch map. P is uniformly expanding if there exists C positive, lambda positive, such that for every x in I, if x, the space of orbit f of x, fn minus 1 of x does not belong to the boundary of the partition. By the boundary, I mean the boundary of the partition elements. Then fn prime x is bigger than C E lambda n. This is just saying that the derivative is bigger than 1 in some sense. Everywhere in the interior of these partition elements is away from 1. And these maps, like the Gauss map, the decimal expansion, they have this property. So let's write this theorem. So let F be uniformly expanding. So uniform expanding full branch map if, so this is the condition that would imply the supremum of omega in P, the supremum of xy in omega. This doesn't, it's just a way to get rid of one supremum, okay, which is n, which makes this condition difficult, I think, difficult to check, of f double prime x over f prime y squared is finite. If this is finite, then we say that then f has bounded distortion. Then f has BD. Okay, so this is a condition that would imply bounded distortion. So in particular, if you have your full branch map, you can just look at this quantity in the partition elements. You don't need to go to n's, okay? So this. I forgot to say that for kx mod 1, for instance, for the decimal expansion, you can really, for the decimal expansion, this is 2n, this is 2n, so this is 0. The bounded distortion is obvious. This is 0 because for 2x mod 1, this is 2n, this guy is 2n, so this is obvious. For 2x mod 1, for also kx mod 1, it is obvious. So all those linear full branch expanding maps, this theorem implies ergodicity. Because Lebesgue, this theorem and the remark here. Because for those, okay, you don't need this remark actually, sorry. Because Lebesgue is ergodic, is invariant, sorry, I'm very slow. Lebesgue is invariant if you have linear branches and they have bounded distortion, then they are ergodic. So let's prove this theorem here. Yep. So the proof is a little bit, it's not difficult, but just a lot of calculations. So this, in the literature, you can see this is called Rayleigh condition. It is used in many studies in one-dimensional dynamics. Because bounded distortion is crucial when you want to study anything in one-dimensional dynamics, like finding these measures or these physical measures and stuff. You need a bounded distortion condition.
In complex dynamics, when you need to prove that, like the Lebesgue measure of a Julia set of a polynomial that has some hyperbolic
Yeah. Bounded distortion, yeah. Yeah. Yeah, it's very, very much used in dynamics. Because usually when you study dynamics, the way what you do is you said I want to know the feature of orbits. Let's say I want to know until 1,000 iterates. So what do is I chop my space into pieces that stay together until 1,000 iterates. So instead of having these uncountable points to check, you just have these omega n's which are finite, okay, in some cases, okay, which are just finite. So you do this chopping. You said I stop at 1,000 iterate, and I just want to know what happened for 1,000 iterates. I chop, and I just consider the bits that stay together until 1,000 iterates. Now, if I want to know more 1,000 plus 1 iterates, I need to do more chopping to my space. And to do more chopping, you need to know that ratio. You need to know this ratio, okay? You need to know the ratio that you're chopping, okay? And this property is telling you that doing the chopping in this small bit is the same as doing the chopping at the final when the interval is the whole thing. Like you take fn, you iterate it. So you have that fn of omega n is the whole interval I. So when you want to do the chopping for n plus 1, you can do it here, which is like you instead of like doing a chopping of a small of this guy, you can do it here, and the amount you chop will be the same as the amount you should chop here by this property, by this bounded distortion. So it's really very good to have it when you want to study dynamical system. Okay, so what do I wanted to prove this, because once we have this condition, I want to do this proof because it's using a property that in the proof you will see a property that is also very important in dynamics using expansion. So I'm in one dimension, so see that fn prime of x equals f prime at fn minus 1 x, f prime at x, okay? This is just the property of this one dimensional for the derivative, okay? So if I take 2 points, I erased the bounded distortion. So let me just write here, we were looking at fn prime x over fn prime y, okay, where x and y, they belongs to the same omega n. So you take xy in omega n, and you compare this to these two guys. So you can see that log of fn prime x over fn prime y you can see this as a sum. So first of all, you can write as of product I equals 0 n minus 1 f prime at fi x over f prime at fi y, okay, like this, just using that above. So for simplicity, let's write this xi to be just do for notation fi of x and yi equals fi of y, just for notation. And this is the sum for I equals 0 n minus 1 of log of f prime at xi minus log f prime yi, okay? Just using the property of the log. Now from here you can use a mean value theorem here. So this is the sum I equals 0 n minus 1. So you use mean value theorem for this function. You take u gives log of f prime u. Okay, so you have this function at xi minus this function of yi. So it is like the derivative somewhere in between. So this is, and the derivative of this will bring f double prime of a point xi over f prime xi times xi minus yi. Okay, so I use this where xi is in this interval. Xi is in xi. Okay, I'm being a little bit not. So these points, they are on omega n. So they stay together, and the image is again an interval. I can assume that. So xi is in this interval. Okay, is in the interval xi yi, because in practice I don't know which one is bigger, but you understand what I mean here. It's just a point in between. Okay, xi is a point in between. All right, and then see that this, if you take j, if you write j as this interval, the interval given by xy, this is the size of fi of j. Okay, so xi minus yi is fi of j, the size of fij. Okay. F double prime xi over f prime xi fi of j. Okay. Here is a crucial point when where I need to use the expansion, okay? Because this is what I want to do. Let me write something. Equals 0 n minus 1 f double prime xi over f prime xi. This you can write it as f I minus n and fn. Okay, I did nothing, I just add and subtract n. And what is good here is that you can see that this point will be the size of this interval. Using mean value theorem again, it will be less than, it will be bigger than c. So this is what I'm saying. If you use the expanding and mean value theorem, you can see that this is bigger than, or this is less than, sorry, because it's negative here. I equals 0 n minus 1 f double prime xi over f prime xi times, so c is the constant you get, or c minus c, yeah, the constant you get from lambda e lambda to the power I minus n times the size of fnj. Okay, let me see the notation if I'm having all the notation correct. Yes. 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 All right. So do you see this step, the fact that this guy, this step, because so this will be bigger than the derivative of this guy at some point times this size, but the derivative is small in n by this factor because this is negative. Okay. Is this clear? Can you follow this? Or maybe let me explain it better there. So what I'm using here is that you have f minus j, if you want, of an interval omega, this guy. What is this? This is f minus j prime at some point xi in the interval times omega, where xi is a point in omega. Okay, this is just mean value theorem. And this guy, by expanding, is less than c e minus lambda j. Okay, times size of omega. So that's what I use there. So if I continue here, you would have log of fn prime x over fn prime y. So this is the sum of f and f double prime xi I over f prime xi I. So c e minus lambda n minus I if I want. And f and j is a subset of I, okay? F and j is a subset of I. This guy here is a subset of I. So this is less than the size of I. So I should put it there. Times the size of I. So the whole proof is just to see what condition for this to be bounded independent of n. Okay. Let me see if the notation is okay. Yes. I minus theta. Yes. I think I yeah, I think I I think I did something a little bit faster. This is what you would do if you wanted just to check without the square here, okay? But let me, I'm sorry, that's my bad. So here what I want to say is it is f minus n minus I prime of some theta times the size of, just mean value theorem, okay? Sorry, I went a little bit fast. Sorry, yeah, these are the C. And if you want, you can write equality. And here theta is just a point on the interval. Theta is just on I. Okay? Yeah, so, yeah. Sorry. Yeah, this is the property I use. Yeah, let me rewrite it because, yeah, I was going a little bit fast. That's not good. F double prime xi I over f prime xi I times f minus n minus I theta times the size of f n j. Okay? Yes. F minus n minus theta. Yes. Yes, and at this, let me see, before I do something different than what I wanted to do. Yeah, so here so there is just one step because, I was saying that this is the type of condition. What I did first is when you have this uniformly bounded or, but with a square here, this is tricky. With a square, since I'm dealing with expanding map, it's easier to check this. This implies that the one without. So if you have the one without the square here, it implies this with the square is also bounded because this is bigger than 1. So this is weaker. Okay, this is much weaker. Okay, yeah. So what I was doing there is not quite correct. So here what you do now is so this guy you can write it as f minus 1. Let me use the same notation, f minus 1 prime at z times f what do I want here? F minus n minus n minus I plus 1. So what I did, I just take out 1 here of theta. Yeah, this is a trick to do here, which helps to get one more derivative down here. And this z will be on fi on z is in fi of j, which is the same where this guy is xi I. Okay. Yeah, and at this step now you use. Okay, I forgot there is the size of I here. Sorry, I'm going a little bit crazy here. So this is less than the size of I because it's a subset of the interval. And from here, so now it's an inequality. Now you can use the expansion because, so this is really tricky here. This step before you use the expansion, you need to get one derivative that can help to get this bounded because you will have this will come down here as a square, okay, or the maximum between the two. F double prime xi I. This is the maximum. Yep. The maximum between f prime xi I and f prime z times this guy. Now you can use the expansion minus lambda n minus I plus 1. And now the crucial observation here is that if you put this out, you replace it by the maximum, by the supremum of xi, and here you can have the square because the supremum you have it here in the below. Okay, so this is less than ci supremum of f double prime x over f prime y squared sorry, that's a square, the maximum square, the sum of e minus lambda n minus I plus 1. And this is uniformly bounded. This is a geometric series, so this is bounded whenever you have this bounded. Okay, yeah. Yes, sorry, it was a little bit confusing here. So there is a step here which is helpful. You know, yeah, at this point it makes me think now which one is better, which condition is better, because you can put, if you want, okay, you can, it makes me think which one is better, yeah, I don't know. So you can see the first argument that I was doing, what it would use is the supremum over f prime, double prime of x over f prime at x, the same point, versus the supremum of f prime of x over f double prime of x over f prime y squared. Which one is better? Actually, I cannot say. It depends. Okay. So from what we see, both implies bounded distortion. Okay. For this, you don't need to do this step. You don't need to use this z for that condition. For this one, you can just do mean value theorem for what I was doing before. So both implies bounded distortion. And yeah, it depends on which one you want to use. Yeah, both of them, they implies bounded distortion. Yes. Yeah. Yeah, I remember, yeah, now that I remember this, thinking about these two conditions. This is a linear condition. This one is also nice because it's at the same point. And for instance, I think there are many systems that it's easier to check this one. Because if you have infinite derivatives somewhere, this guy might create problem. This is just a supremum over x, and this is a supremum over x and y, okay? And you might have points where this is infinite y. Okay, so this blow up. So yeah, so if you have infinite derivative, maybe this one is better. If you have some singularity for your dynamics. Like, anyway, let me not say more on this. Let me not say more on this before I. So there is this topic that I wanted to say for a presentation. Is that every full branch expanding map has a unique measure, has a unique invariant measure every full branch expanding map with bounded distortion, sorry. BD has a unique measure that is absolutely continuous with respect. It has a unique invariant measure that is absolutely continuous with respect to Lebesgue. Okay. Every full branch expanding maps with boundary distortion has a unique, yeah. Actually, with these conditions, what you can prove, actually, you can prove that if you take the Perron-Frobenius operator Pf of any potential, it is converging to some phi star, and this guy is the define the invariant measure, okay? And mu star equals phi star dm, d lambda or m, d Lebesgue, okay? Yeah, this involves, using some Banach spacers and stuff, prove that this is a contraction. And it is invariant and it is ergodic. Actually, this implies mixing. We will see later that this implies mixing. Yeah. To read about this, the good reference is the book that I said last time, the book on fractals, chaos, and noise by Mackay and Lazota and Mackay. Yeah. So one exercise is to is that the Gauss map has boundary distortion. I mean, it's just easy to check. Gauss map has boundary distortion. And this, and in particular, it implies that the Gauss map, the measure that we defined last time, I mean, a few lectures back, is ergodic because it is absolutely continuous with respect to Lebesgue. And yeah. So so this is a way to prove ergodicity for expanding maps, proving boundary distortion, finding the measure that is absolutely continuous with respect to Lebesgue, and that measure will be ergodic. For next lecture, I will do the Bernoulli shift, the shift maps, which is a good example also to study dynamical system. And then we will do also, I will explain the Hopf argument, how to prove ergodicity for general dynamical system when you have some hyperbolicity, because for one-dimensional maps, this is really a good way to do it if you have expansion. If you don't have expansion, the example we see is a circle rotation, which is very particular. And yeah, if you have expansion also, I mean, if somebody wants to study more, like you can just, as a project, you could project like for a master or something, you could remove like full branch map on the definition. Just assume that you have expansion, maybe not uniform everywhere, and try to recover, try to get this, to do the chopping, try to find this partition, and then prove ergodicity. That is something very important. Like you have a dynamical system on the interval that is piecewise smooth, okay, smooth except countably many points, and you have this condition. There is a way to do the chopping to find the partition and then check boundary distortions and stuff. That will be something good, maybe not for a presentation because that will require a little bit more work, but this would be good for a presentation at the end as bad. So this is for expanding one-dimensional dynamics. For higher dimension, I will explain the Hopf argument, maybe not next lecture, the lecture after. So for the next lecture, we will study symbolic dynamics. Okay, so I will stop here for today.